This talk is devoted to studying under the title Recovery of Mutual Information by Inhomogeneous Quenches into Dimensional Conformal Field Theories. Dr. Nozaki, you have 30 minutes and
okay,
5
thank
minutes
you.
for the questions. And
Okay. So, can you hear me? Hello? Hello?
yeah, hello. Yeah, we have hear you
Okay.
loudly and clearly.
Okay, thank you. Okay, so thank you for the introduction and thank you for giving me an opportunity to present my recent works. So this talk is based on the collaboration with Kanato Goto, Shinsei Ryu, and Mao Tiantan, and Kotaro Tamaoka. This is work in progress. So first of all, I will explain the abstract of this talk. So our motivation on this talk is to recover a quantum property from the typical state. This is a state doesn't have any quantum property. And how to do it is that we evolve the system with an inhomogeneous Hamiltonian, and this Hamiltonian has that Hamiltonian can correct the quantum information to some special point. And the setup we consider is that evolve the system in the thermofield double state, and this thermofield double state is approximated by the product of the Bell state with 2D holographic Hamiltonian, then evolve it with the sine-squared deformed Hamiltonian. This is the abstract of my talk. And let me explain the, first of all, let me explain the process of scrambling and the property of the typical state and the target state. Target state is that state that we want to create. Scrambling is one of the cutting-edge research topics, I think, and this is closely relevant to the quantum summarization. And let me prepare the initial state, phi naught 1 and phi naught 2 and phi naught 3 like this. And they are depend on the initial condition. Also, local observable in A depend on the initial condition, and we evolve this system with time evolution operator. And also, then of course, the time local observable in A depend on time. And for specific Hamiltonian, and in the very large time region, state can be up. For specific Hamiltonians, so reduced density metric for this late time state can be approximated by this. This is a reduced density matrix for the thermal state. The property of this state is this reduced density matrix associated to A is independent of the initial state. This means that this state is independent of the entanglement structure of the initial state. So information on the initial states is locally hidden or effectively lost. So this is the process of information scrambling. And I would like to also comment on the quantum summarization. So quantum summarization is the summarization of the subsystem. This also occurs under this time evolution because the reduced density metrics are approximated by the thermal state with the effective temperature. And people believe that if the Hamiltonian has a scrambling ability, information scrambling occurs. So I explain the process of the scrambling. Next, I'd like to explain the property of the typical state. After the quantum summarization occurs, or after the information scrambling occurs, the system is well described by the typical state. And for this state, entanglement entropy follows the page curve. Here, L and small la denotes the system size and the subsystem size and the dimension of the Hilbert space. And this is a page curve. So entanglement entropy is given for if subsystem size is smaller than the L over 2, entanglement entropy proportional to the subsystem size. On the other hand, if subsystem size larger than the L over 2, this is proportional to L minus LA. And for this state, the non-local correlation, which is measured by the mutual information, and in this parameter region, so in this parameter region, the size of the subsystem A and B and A cap B is smaller than the half of the total system. In this parameter region, mutual information is approximated by 0. And this indicated that reduced density matrix for A cap B is factorized into the rho A times rho B. And this property of this state is that A and B is uncorrelated. Because if you compute this two-point function factorizes into the one-point function. So there are no correlation between A and B. So this is a property of the typical state. And finally, I'd like to explain the target state. So this state is a state we would like to create. And you may ask me, so how you can extract the quantum nature of the state from the typical state? And more precisely, you may ask how you can retrieve non-local correlation of the state from the typical state. And what we want to do is as follows. So first we prepare the typical state, and we evolve it with some Hamiltonian, and we would like to make a atypical state. And the property of this typical state is that the mutual information becomes positive even for this parameter region. And this indicated that the rho A cap B does not factorize in the rho A times rho B, and there are non-local correlation. This is what we want to do. And this is a target state. So this is what we want. This is a state which we want to create. And this retrieval may lead to the information retrieval from black hole or quantum cooling or quenches, where we can prepare the state of interest. Okay, let's move on to the how to do it. So to explain it, I would like to explain the correcting effect of the sine-squared deformed Hamiltonian. So you may ask, how do you achieve this information retrieval? And our answer is that we use inhomogeneous quenches, where we evolve the system with Mobius or sine-squared Hamiltonian. And I will explain the details of this Hamiltonian later. At this moment, I'd like to explain the property of this Hamiltonian. So why we would like to use this? Answer is as follows. So in the scrambling, quantum information is delocalized and locally hidden. On the other hand, during the evolution by the sine-squared deformed Hamiltonian, the quantum information may be localized. So I'd like to explain why we can think so. So as a simple example, let's consider the following setup. Let's start from the thermal state, and then evolve it with the SST Hamiltonian. And we divide Hilbert space into the A and A bar. And we assume that A includes the origin. Then the time evolution of the entanglement entropy for A is shown in this plot. So, and this plot shows that entanglement entropy monotonically increases, and finally entanglement entropy is approximated by the thermal entropy. This is the entropy for the total system. And this result shows that the amount of the entanglement entropy for A is approximated by that of the total entropy, and we can interpret that all the degrees of freedom or quasi-particles accumulate around the x equal origin. So SSD Hamiltonian may have a localized or correcting effect to the origin. So I explained the correcting or localizing effect of the sine-squared deformed Hamiltonian. And so this effect is opposite to the scrambling effect. So we may control the scrambling effect by this localizing effect. So we can extract the non-local correlation from the typical state. And finally, I'd like to explain the details of our setup. The system we considered in this project is as follows. So we start from the thermofield double state. So thermofield double state is defined on the doubled Hilbert space. And we act Hamiltonian only on the Hilbert space 1. And for system 1, we evolve this state by this time evolution operator. This time evolution operator for the Mobius quench and SSD quench. And in the system 2, we evolve the system by with the uniform Hamiltonian. Then we evolve the system with the SSD Hamiltonian. This is the system 2. And system 3 is opposite to this system 3. System 3 is opposite to the system 2. So first, we act with the time evolution operator on, time evolution operator for SSD on the TFD state. Then we evolve the system with the uniform Hamiltonian. But I think I don't have time enough to explain all the results. In this talk, I consider only this state. And this is our strategy. So we evolve the system with 2D holographic Hamiltonian. And people believe that 2D holographic Hamiltonian has a strong scrambling effect. Then this Hamiltonian destroys the mutual information completely. Then we evolve the system with SSD holographic Hamiltonian. And if this Hamiltonian has a localizing effect, maybe we can get the non-local correlation, or we can check whether the non-local correlation is recovered. This is our strategy, or this is what we want to consider. And this is this state this system is a detail of the setup. Okay, this is the contents of my talk. Next, move on to the summary. Then after that, I'd like to explain the detail of our result for system 1 and system 2. Then finally, I would like to discuss on our result and comment on the future direction. But before going to the summary, I have two comments. One of them is as follows. The parameter region considered in this talk is this. And L, large L and small l and T and epsilon is a dimensionless parameters. And their unit is a lattice spacing. And L, small l, T, epsilon denote the system size and subsystem size and time and inverse temperature. We consider this parameter region. And another comment is that all the theory considered in this talk are two-dimensional conformal field theories. This is my two comments. Okay, let's move on to the summary of our project. So first result is a non-local retrieval by using the inhomogeneous quench. So this is the main topic of my talk. We evolve the system with 2D uniform holographic Hamiltonian, and we consider the time region where T naught is much larger than L. Then the system may be approximated by the typical state. So entanglement entropy follows the page curves. As a consequence, mutual information between A and B is approximated by 0. And here, subsystem A is defined on the H2, and subsystem B is defined on H1. Then we evolve it 2D SSD holographic Hamiltonian. So then we found that the non-local correlation is recovered from the typical state if B includes the origin, because IAB becomes initial value, and this proportions the subsystem size. This is the main result of my talk. And following is just a comment on the other result. So result 2 is the property of the untypical state. Our motivation is whether the correlation created by the SSD time evolution is robust against the 2D holographic time evolution. To check it, we evolve it with the 2D SSD holographic Hamiltonian and then evolve it with 2D uniform Hamiltonian. Our answer is yes, this correlation is robust against the 2D holographic time evolution. Even during the evolution by the Hamiltonian with strong scrambling ability, the late time state has quantum nature because the entanglement entropy, the mutual information oscillate in shows the oscillating behavior with time. This correlation is robust against the 2D holographic time evolution. And the third result is a genuine tripartite entanglement. So we consider the large T1 region. And in this region, the system 3 has one amazing property. Let's divide H1 into the B1 and B2 and complement to them. And let A denote the subsystem of H2, like this. And we compute the mutual information between A and B1 or A and B2. They are approximated by 0. And we also compute the mutual information between B1 and B2. It is approximated by the 0. But if you compute the mutual information between the A and the union of B1 cup B2, the time evolution of the mutual information for this case show non-trivial behavior like this. So this result indicated that this atypical state have a following property. There are no correlations shared by the two parties, but there are correlations shared by the three parties. So this is a very amazing property for me. And I also studied we also studied wormhole growth in the atypical state by using this quantity, and this plot shows the time dependence of this quantity. And if T1 is small, here we consider the third case. Then first we evolve the TFT state with SSD Hamiltonian, and then we evolve the state with uniform Hamiltonian. And so this T not for the uniform Hamiltonian. And if T1 is very small, this quantity linearly grows as usual. But if T1 is very large, so this quantity grows non-linearly, like a step function. And we also propose one physical interpretation which can explain this time evolution. But I think I don't have any time to explain the detail of this model. So anyway, the main contents of my talk is this. Okay, so let's move on to the detail of our project. First of all, I would like to explain the Mobius and sine-squared deformation. So the definition of the Mobius and sine-squared deformation is as follows. First of all, we look at this equation, and Hx is an energy density, and Fx is an envelope function, and Fx equal 1. If Fx equal 1, this Hamiltonian is a usual uniform Hamiltonian. And for Mobius case, this envelope function is given by this. And SSD case, envelope function is given by the sine-square function. And if you take theta to be 0, this Hamiltonian reduces to the usual Hamiltonian, uniform Hamiltonian. And if you take theta to be infinite, this Hamiltonian becomes SSD Hamiltonian. And we would like to know the evolution of the primary operator in the Heisenberg picture under this evolution. And the evolution of the primary operator by this Hamiltonian is given by this. So this looks like a conformal transformation of the primary operator. And I forget about the one comment. So we consider the finite system, and in this talk we consider the spatial circle with L. This L denotes the circumstance of spatial circle. And one of the important property of this Hamiltonian is that during the time evolution by inhomogeneous Hamiltonian considered in this project, the operators move along the spatial circle. Let me explain it. So let's define the spatial position of the local operator by this. This is, and under the SSD evolution, if operator is at the x equals 0 or x equals L over 2, x nu does not move. So we call them fixed point. On the other hand, if operator is act on if operator acts at the spatial point except for the origin or L over 2, they move along the spatial direction, and these operator move from this point to the L over 2. So this arrow shows the trajectory of the operator under the SSD time evolution. Okay, so next I'd like to explain how to compute entanglement entropy in the path integral formalism. So this is a recipe to compute the time evolution of the entanglement entropy. First of all, let's define the Euclidean density operator in the Euclidean space. Next, we would like to compute this quantity in the path integral formalism. And this is given by the partition function of the n-shaded geometry. And the n-shaded geometry is given by the thing and copy of this geometry together along the subsystem A, like this. So you can get, in this picture, we only consider n equal 2 case. So by computing the partition function on this geometry, you can compute this quantity for n equal 2. And by employing the twist operator formalism, so replace the this partition function with the okay. Can I start?
Yes.
Sorry, can I? Ah, okay. Okay, then. So I'd like to finalize my talk. So the message of my talk is that the entanglement entropy is given by the two-point function. And after getting two-point function, we analytic continue to real time, then we can get the time dependence of the entanglement entropy. And let's focus on how to compute the correlator. So we have two ways to compute the correlator. One of them is showing a picture. In this picture, state depends on the time. And before analytic continuation, Euclidean geometry is non-trivial, so computation becomes difficult. On the other hand, in the Heisenberg picture, local operator evolve in the time, but the state itself is independent of the time. Then we can compute entanglement, and if we know if the transformation of the time evolution of the operator is simple, we can compute the two-point function easily. And for this case, for Mobius Hamiltonian or SSD Hamiltonian, the Heisenberg operator is very simple, like a conformal transformation of the primary operator. Then we can compute entanglement entropy easily. And here we consider the entanglement entropy for subsystem B on the H1. And only this piece depends on the detail of the theory. And in this parameter region, this quantity is given by, in the ADS CFT correspondence, this quantity is given by the geodesic length associated with B on the PTZ black hole geometry. And this piece is much larger than this piece, and this quantity is approximated by this term. And as a simple example, we consider this situation. So I will explain why SB becomes S dot when B included in the X includes the origin. in this parameter region, this quantity is approximated by this, and this is given by the geodesic, which corresponds to this blue line. And x nu denotes the location of the operator, and this quantity, the time dependence of entanglement entropy, this quantity is determined by the evolution of the operator. And this red arrow denotes the evolution of the operators. And finally, operators approach to this point. Then this contribution becomes smaller, then so entanglement entropy increase like this. And finally, this piece vanish because this distance become very small. So entanglement entropy is approximated by thermal entropy. And I think I don't have time to explain all the results. Sorry. So the main point is that even for system 2, we evolve the thermofield double state with the 2D holographic Hamiltonian. Then we evolve the system with the SSD Hamiltonian. Then we found that mutual information returned to the initial value like this. And the entanglement entropy changed disconnected piece and the connected piece under this time evolution. And this is a summary of my talk, but I think I don't have time I don't have time to explain this slide. So this is a view of the futurization. Thank you for attention.